All right, so here we go. Chapter 8. We have sequences, series, and probability. So these first few sections are the sequences and series, and then the last few sections are the probability. So those of you going into AP Stats, the probability will actually be helpful for you. If you're going into Calc, none of this will really be that helpful for you. But you know, it could though be helpful for you though on the SAT. Like some of this stuff could show up for you on the SAT. So before we really get into all of chapter 8, there's just some background that maybe was missed from Algebra 2 that either got skipped or got taken out. But just a few things we feel like if we go through these now, then it will make the rest of the chapter a little bit easier for you as we get more into them. The first part with the sequences series, explicit and recursive formulas. So kind of your formal definitions of what each of these things are. When the book is talking about a sequence, it's just an ordered set of numbers. You have different terms. So your first term of a sequence, your second term of a sequence, your third term of a sequence. So you'll see the sequence written just as an ordered set of numbers. A series, though, is the sum of a sequence. So if you don't have a sequence, you can't have a series because you have to be able to add up the terms of your sequence in order to get your series, which would be the sum of a certain number of terms of your sequence, or potentially an infinite sum of a sequence. Your explicit formula is written so that you can find any term in the sequence. And if you look at your formula sheet that you should have picked up, your formula sheet has a couple different types of explicit formulas on it. One is under your arithmetic sequence, and one is under your geometric sequence. So the idea with the explicit formula, when you have the explicit formula for that one, you're going to plug in your term number. So if you wanted to find the fifth term, then for an explicit formula, you would just plug a 5 in for your n because you're looking for the fifth term. The recursive formulas, you always have to know the previous term. So in a recursive formula, you're always plugging in the previous term. So recursive are a little bit more tedious because you have to always have the term before it to get the next one, where with an explicit, if you have the formula, you can find any term you want. All right, so starting with an arithmetic sequence. So an arithmetic sequence has a constant difference between each term. So you can think about for an arithmetic sequence that you're adding or subtracting the same amount each time. So the same amount between terms. And they call that the constant difference between terms, which we use the letter D to talk about the constant difference. So your explicit formula for an arithmetic sequence is right here. And the way you write your explicit formula is we say A sub n. So n will be the term number, but if we're just writing a formula, we leave it as an n so we could find any term number. You start with your first term, and then you add the difference times the quantity of n minus 1. So it's kind of like writing an equation for a line where you're plugging in the slope and the y-intercept, and then n is like the x, where that will just stay a variable. And then your recursive formulas have the little bracket on them like this. You always have to list the first term, because if you don't list the first term, you can't find the next term. And then you write it as a sub n minus 1, so that n minus 1 is in the subscript. It's not the same as this n minus 1. Like it's not up in the equation. So this a sub n minus 1 just means the previous term. Because if you think about subscripts, right? If we had that the first term was something and we wanted to find the second term, 2 is our n. So if we were to plug it in, we would say that a to the 2 minus 1 plus d, whatever our difference is, which would mean that we're taking the first term plus the difference, right? And the first term is the term before the second term. So that's all that means. It just means plug in the term value from the one before it. All right, so we have two different examples of sequences. The first one is 2, 5, 8, 11. And then the next one is 100, 90, 80, 70. Do you see those up there? So we're going to write explicit and recursive formulas for each of those. So for the first one, which we'll call A, if we were writing an explicit formula, and remember your explicit formula is your A sub n equals the first term plus the difference times n minus 1. So we would say A sub n equals, what's the first term of this sequence right here, that first sequence? 2. So we 2 plus, and then you would think, what's the difference? What do you do to get the next term? We're going to add 3. So our difference is 3 times n minus 1. And then we simplify that. So you're going to distribute the 3. So you would have A sub n equals 2 plus 3n minus 3, or A sub n equals negative 1 plus 3n. And so if you wanted to find the 100th term, you'd plug a 100 in for n, and you could get the 100th term. So that's your explicit. If you wanted to find the recursive, so your recursive always starts by writing the first term, which we know is 2. And then we say to get the next term, we need to have the previous term, and you don't actually write the previous term, you just write it as A sub n minus 1, which means take your previous term and add 3. And then we can say for when n is greater than or equal to 2, which just means that works for all the terms, like this terms greater than or equal to 2. So the second term, the third term, the fourth term, the fifth term. All right, so let's move on to a geometric sequence. So a geometric sequence has a constant ratio, which we call r. So a geometric sequence, you either multiply or divide by the same value to get your next term. Okay. So some sequences will be arithmetic, some will be geometric, and some won't be either. They'll have different patterns to them. So there are two formulas again, your explicit and your recursive. Those are on your formula sheet, so you don't have to have them memorized. And it would probably make sense that the ones that have r's in them go with geometric because the r means ratio. The ones with d's go with arithmetic because the d means difference. All right, so your formula for your explicit formula is your first term times the ratio raised to the n minus 1. And your recursive formula is your first term, and then the next term, this should have said, fix that, A sub n minus 1 times the ratio. That's a little typo there. I think your formula sheet, though, is correct, so I imagine you'll be looking at that more. All right, so let's look at this example right here where we have the sequence that's 100, 50, 25, 12.5. So if you start to look at the pattern of that, you realize that you're dividing by 2 every time, which means that your ratio for that would be 1/2. Because you really have to think, what are you multiplying by to get your next term? You're multiplying by 1/2. So if we were to write our explicit formula, we would say A sub n equals the first term, which is 100, times the ratio, which is 1/2, to the n minus 1. Okay, an order of operation says that you have to do the exponents before you multiply, so you can't combine this 100 and 1/2 and make it a 50. It just has to stay that way. You would have to raise the 1/2 to the power first before you multiply it by 100. And then your recursive formula, we would say that the first term is 100. And if you wanted the next term, you would take the previous term. So that's that a sub n minus 1. Make sure that n minus 1 is down in the subscript. Times the ratio, which in this case is 1/2. We would say that works for terms greater than or equal to 2. So n is greater than or equal to 2. All right, so moving on to other sequences. So some other sequences that you could potentially have to look at are Fibonacci sequence. So with Fibonacci sequence, that's the one where you have to have your first two terms, and then the next term would come from adding the two before it. So if we were writing out Fibonacci sequence, we would say the first term is 1, the next term is 1, and then it says the next term is the one before it and the one before that. So if you were to add the two before it, you would get 2. And then the next term would be 3 because we would have to do 1 plus 2 and we would get 3. And then the next term would be 5 because we would do 2 and 3 and we would get 5. Right? So that would be your Fibonacci sequence. And then you have another formula that generates triangular numbers. And what a triangular number is your first term is 1, your next term is 3, your next term is 6, and it forms these triangles. So what happens is every term you take all of your rows, but your fourth term, so in that fourth row, you would end up adding 4 dots. So that's the formula, the previous number plus n. So it's just whatever term you're on. So those are kind of two examples that wouldn't necessarily fit your geometric or your arithmetic sequences. All right, factorials. So this always shows up on your ACT or SAT. So this is something good to learn about if you don't have knowledge of it yet. The factorial, or that exclamation mark, is just the product of all of the natural numbers. So natural numbers are your counting numbers, so they start at 1, and you just keep going all the way down. So if we needed to find 4 factorial, we would say 4 factorial is just 4 times 3 times 2 times 1, which would equal 24. And 12 factorial would be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5, 4 times 3 times 2 times 1. All right, and the good news with something like 12 factorial, in your calculator, if you go to your math button and then over to your probability, there's a factorial in there for you. So if you need one that's a bigger number, you could just type 12 and then math, go over to probability, and go down to number 4 and hit your exclamation mark, and you would get the value of 12 factorial. So moving on to Pascal's triangle, and this is kind of the last thing that we're going to talk about today. But Pascal's triangle is the tool that we use to help us expand binomials. And it will also help us when we get into the permutations and the combinations with the probability. So in general, this is kind of the rule here. In general, the nth row of Pascal's triangle give you the coefficients of x plus y to the n. But you're not always going to have this nice x plus y to the n. So we're going to work our way through expanding. So the way that Pascal's triangle works is that it always row 0. So this top row is your row 0. And then the first row, row 1, is actually kind of that second row. Because row 3 is going to correspond to the row that has the 3's in it, right? Row 4 is going to correspond to the row that has the 4's in it. Row 5 would be 5, okay? And so then what you do is you just add these two numbers together, and it gives you that number. So like 1 plus 2 would equal 3. 3 plus 3 would give you 6. 4 plus 6 would give you 10, right? So you can always figure out what that next row is. So as long as you know these first two rows, you should be able to figure out what the rest of the rows are, because you could just come up with them, right? Adding the numbers above them. So if we want to expand this x plus 2 to the fourth, that means that the fourth tells us that we're using the row with the 4. So we're using the 1, the 4, the 4, and the 1. And so we need to write that down. So we're going to go through this process of this foolproof way of expanding a binomial without actually having to FOIL the whole thing out 4 times. So we have the 1 plus 4 plus 4 plus 1, right? Oh, I skipped the 6. Well, come on. The 6 is kind of important. So we'll put the 6 in there, and then the 4, and then the 1. Okay. So then what we do is we take this first term. Oh, I'm on erase. We take the first term, which is our x, and we put it underneath the 1. So we're going to say x to the fourth. And then we're going to keep going down, and then we're going to say x to the third, x squared, x to the 1, and x to the 0. Okay? Then we're going to take our second term, and we're going to go the opposite direction with it with the exponents. So we're going to go 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. Okay. And then what we're going to do is we just multiply these columns, and those are each of our terms. So what's 1 times x to the fourth times 2 to the 0? Just x to the fourth. Then we do our next column here. So 4 times, so I would look at your numbers. 4 times 2 is 8. So now we'll have plus 8x to the third. We can do our next column. So we'll have 6 times 4. So we'll get 24x squared. And then we have 4 times 8. So we get plus 32x plus 16. And remember that x to the 0 is 1. All right, let's look at this next one. So it's a 3, which means we're using the 1, the 3, the 3, and the 1 row, right? Because we have the 3, so we have to use that third row. We take this first term, the 2x, and we have to do the whole quantity. So we'll have to do 2x to the third. So the 2 and the x both have to be cubed. And then we'll have our 2x squared, and then our 2x to the first, and then our 2x to the 0. And then we'll take our -3 and we'll do the same thing. So we have -3 to the 0, -3 to the 1, -3 to the 2, and -3 to the 3. And then if you start multiplying in your columns, you have 8x cubed for your first one. And then you'll have 3 times 4 times -3. Or you could think 9 times 4, which would be 36, and it's negative. So we're going to have negative 36x squared. And then here we'll have 3 times 2 times 9. So we have plus 54x. And then here we'll have negative 27. And that's it. So minus 27.